An interpretation of quantum mechanics is a set of statements which attempt to explain quantum mechanics. Although quantum mechanics has held up to rigorous and thorough experimental testing, many of these experiments are open to different interpretations. There exist a number of contending schools of thought, differing over whether quantum mechanics can be understood to be deterministic, which elements of quantum mechanics can be considered real, and other matters. This question is of special interest to philosophers of physics, as physicists continue to show a strong interest in the subject. They usually consider an interpretation of quantum mechanics as an interpretation of the mathematical formalism of quantum mechanics, specifying the physical meaning of the mathematical entities of the theory. History of interpretations. The definition of quantum theorists' terms, such as wave functions and matrix mechanics, progressed through many stages. For instance, Erwin Schrödinger originally viewed the electron's wave function as its charge density smeared across the field, whereas Max Born reinterpreted it as the electron's probability density distributed across the field. There was detailed and vigorous debate about this and many other related questions at the Fifth Solvay Conference in 1927. Debate has continued right to present times. An early interpretation has acquired the label Copenhagen interpretation, and is often used. Amongst more recent interpretational concepts are quantum decoherence and many worlds. During most of the 20th century, collapse theories were clearly the mainstream view, and the question of interpretation of quantum mechanics mostly revolved around how to interpret collapse. Proponents of either pilot wave or many worlds interpretations tend to emphasize how their respective camps were intellectually marginalized throughout 1950s to 1980s. In this sense, all non-collapse theories are minority interpretations. However, since the 1990s, there has been a resurgence of interest in non-collapse theories. The Stanford Encyclopedia as of 2015 groups interpretations of quantum mechanics into Bohmian mechanics, collapse theories, many worlds interpretations, modal interpretation, and relational interpretations, as classes into which most suggestions may be grouped. As a rough guide development of the mainstream view during the 1990s to 2000s. Consider the snapshot of opinions collected in a poll by Schlosshauer et al. At the 2011 Quantum Physics and the Nature of Reality Conference, July 2011. The main conclusion of the authors is that the Copenhagen interpretation still reigns supreme, receiving the most votes in the poll. Besides the rise to mainstream notability of the many worlds interpretations, the Copenhagen interpretation still reigns supreme here, especially if we lump it together with intellectual offsprings such as information-based interpretations and the quantum Bayesian interpretation. In Tegmark's poll, the Everett interpretation received 17% of the vote, which is similar to the number of votes in our poll. Nature of interpretation. An interpretation of quantum mechanics is a conceptual or argumentative way of relating between the mathematical formalism of quantum mechanics, mathematical objects, such as wave functions, state vectors, the Schrödinger equation, and the experimental facts of quantum physics, how laboratory devices are used to make observations in empirical investigations, and the physical meaning of the formalism and the experimental facts, in terms of ordinary understanding, and in more philosophical terms. Two philosophical, or more precisely, two metaphysical aspects are relevant. Ontology, claims about what things, such as categories and entities, exist in the world, and what theoretical objects are related to those real existents. Epistemology, claims about the possibility, scope, and means toward relevant knowledge of the world. In philosophy of science, the distinction of knowledge versus reality is termed epistemic versus ontic. A general law is a regularity of outcomes, whereas a causal mechanism may regulate the outcomes. A phenomenon can receive interpretation either ontic or epistemic. For instance, indeterminism may be attributed to limitations of human observation and perception, or may be explained as a real existing may be encoded in the universe, confusing the epistemic with the ontic. Like if one were to presume that a general law actually governs outcomes, and that the statement of irregularity has the role of a causal mechanism, is a category mistake. In a broad sense, scientific theory can be viewed as offering scientific realism, approximately true description or explanation of the natural world, or might be perceived with anti-realism. A realist stance seeks the epistemic and the ontic, whereas an anti-realist stance seeks epistemic but not the ontic. In the 20th century's first half, anti-realism was mainly logical positivism, which sought to exclude unobservable aspects of reality from scientific theory. Since the 1950s, anti-realism is more modest, usually instrumentalism, permitting talk of unobservable aspects, but ultimately discarding the very question of realism and posing scientific theory as a tool to help humans make predictions, not to attain metaphysical understanding of the world. The instrumentalist view is carried by the famous quote of David Merman, "Shut up and calculate." Opinions vary. J.S. Bell was interested in debate along Bohr-Einstein lines, but recognized that important contributors to quantum mechanics were not. He wrote of "Why bother?" as, for example, Paul Dirac. Though for himself he wrote significantly on interpretation, Dirac wrote about the debate, "I was not very much interested. I was more interested in getting the correct equations." Dirac also wrote, "The interpretation of quantum mechanics has been dealt with by many authors, and I do not want to discuss it here. I want to deal with more fundamental things. Other approaches to resolve conceptual problems introduce new mathematical formalism, and so propose additional theories with their interpretations. An example is Bohmian mechanics, which is empirically equivalent with the standard formalisms, but requires extra equations to describe the precise trajectories that it postulates." Challenges for interpretations. Interpretations of quantum mechanics attempt to provide a conceptual framework for understanding the many aspects of quantum mechanics which are not easily handled by the conceptual framework used for classical physics. Abstract, mathematical nature of quantum field theories. Existence of apparently indeterministic and yet reversible processes. Role of the observer in determining outcomes. Distinction between preparation and measurement. Correlations between remote objects. Complementarity of offered descriptions. Rapidly rising intricacy, far exceeding humans' present calculational capacity, as a system's size increases. The mathematical structure of quantum mechanics is based on rather abstract mathematics, like Hilbert spaces. In classical field theory, a physical property at a given location in the field is readily derived. In Heisenberg's formalism, on the other hand, to derive physical information about a location in the field, one must apply a quantum operation to a quantum state, an elaborate mathematical process. Schrödinger's formalism describes a waveform governing the probability of outcomes across a field. Yet how do we find in a specific location a particle whose wave function, a mere probability distribution, disambiguation needed, of existence, spans a vast region of space? The act of measurement can interact with the system state in peculiar ways, as found in double-slit experiments. The Copenhagen interpretation holds that the myriad probabilities across a quantum field are unreal. Yet that's the act of observation. Measurement collapses the wave function and sets a single possibility to become real. Yet quantum decoherence grants that all the possibilities can be real, and that the act of observation, measurement sets up new subsystems. A key interpretational question is posed by Dirac's famous sentences about quantum interference. Each photon then interferes only with itself. Interference between two different photons never occurs. Dirac stops short of repeating this statement for objects other than photons. such as electrons, contenting himself with saying, for particles even as light as electrons the associated wave frequency is so high that it is not easy to demonstrate interference. Dirac was of course well familiar with the concept of electron diffraction by crystals, which is usually regarded as an interference phenomenon. The comments of Dirac surrounding these sentences indicate that he considers them to be interpretive. No experiment can directly test them, an actual particular photon being detectable only once. Quantum entanglement, as illustrated in the EPR paradox, seemingly violates principles of local causality. Complementarity holds that no set of classical physical concepts can simultaneously refer to all properties of a quantum system. For instance, wave description A and particulate description B can each describe a quantum system S, but not simultaneously. Still, complementarity does not usually imply that classical logic is at fault. Rather, the composition of physical properties of S does not obey the rules of classical propositional logic when using propositional connectives. As now well known, the origin of complementarity lies in the non-commutativity of operators that describe quantum objects. Instrumentalist description. Any modern scientific theory requires at the very least a description that relates the mathematical formalism to experimental practice and prediction. In the case of quantum mechanics, the most common description is an assertion of statistical regularity between state preparation processes and measurement processes. That is, if a measurement of a real value quantity is performed many times, each time starting with the same initial conditions, the outcome is a well-defined probability distribution agreeing with the real numbers. Moreover, quantum mechanics provides a computational instrument to determine statistical properties of this distribution, such as its expectation value. Calculations for measurements performed on a system S postulate a Hilbert space H over the complex numbers. When the system S is prepared in a pure state, it is associated with a vector in H. Measurable quantities are associated with Hermitian operators acting on H. These are referred to as observables. Repeated measurement of an observable A where S is prepared in states I yields a distribution of values. The expectation value of this distribution is given by the expression. This mathematical machinery gives a simple, direct way to compute a statistical property of the outcome of an experiment. Once it is understood how to associate the initial state with a Hilbert space vector, and the measured quantity with an observable, as an example of such a computation, the probability of finding the system in a given state is given by computing the expectation value of a projection operator. The probability is then the non-negative real number given by in the context of quantum mechanics. The instrumentalist interpretation refers to the position that there can be no meaningful interpretation beyond the mere instrumentalist description, a position often equated with eschewing all interpretation. It is summarized by the sentence, "Shut up and calculate." Depending on the understanding of the term instrumentalism, the instrumentalist, or shut up and calculate, interpretation may either express pragmatism or radical empiricism or phenomenalism. Concerns of Einstein. An interpretation of the mathematical formalism of quantum mechanics can be characterized by its treatment of some physical or microcosmological problems that Einstein saw in Copenhagenism, such as realism, completeness, local realism, determinism, causality. To explain these problems, we need to be more explicit about the kind of picture an interpretation provides. To that end, we will regard an interpretation as a correspondence between the elements of the mathematical formalism M and the elements of an interpreting structure I, where the mathematical formalism M consists of the Hilbert space machinery of ket vectors, self-adjoint operators acting on the space of ket vectors, unitary time dependence of the ket vectors, and measurement operations. In this context, a measurement operation is a transformation which turns a ket vector into a probability distribution. The interpreting structure includes states, transitions between states, measurement operations, and possibly information about spatial extension of these elements. A measurement operation refers to an operation which returns a value and might result in a system state change. Spatial information would be exhibited by states represented as functions on configuration space. The transitions may be non-deterministic or probabilistic, or there may be infinitely many states. One way of assessing an interpretation is whether the elements of I are regarded as physically real. Hence the bare instrumentalist view of quantum mechanics outlined in the previous section is not an interpretation at all, for it makes no claims about elements of physical reality. The current usage of realism and completeness originated in the 1935 paper in which Einstein and others proposed the EPR paradox. In that paper the authors proposed the concepts of element of reality and of completeness of a physical theory. They characterized element of reality as a quantity whose value can be predicted with certainty before measuring or otherwise disturbing it, and defined a complete physical theory as one in which every element of physical reality is accounted for by the theory. The paper proposed that an interpretation is complete if every element of the interpreting structure is present in the mathematics. Realism is also a property of each of the elements of the maths. An element is real if it corresponds to something physical in the interpreting structure. For example, in some interpretations of quantum mechanics, the Kerr vector associated to the system state is said to correspond to an element of physical reality, while in other interpretations it is not. Einstein was not the active author of the EPR paper, and it did not quite focus on his principal concern, which was about causality. Determinism is a property characterizing state changes due to the passage of time, namely that the state at a future instant is a uniquely defined mathematical function of the state in the present. It may not always be clear whether a particular interpretation is deterministic or not, as there may not be a clear choice of a time parameter. Moreover, a given theory may have two interpretations, one of which is deterministic and the other not. Local realism is an attempt to formulate in relevant mathematical terms the subtle physical, microcosmological, or metaphysical concept of causality. It has two aspects. The value returned by a measurement corresponds to the value of some function in the state space. In other words, that value is an element of reality. The effects of measurement have a propagation speed not exceeding some universal limit. In order for this to make sense, measurement operations in the interpreting structure must be localized. A formulation of local realism in terms of a local hidden variable theory was proposed by John Bell. This is expressed in what is widely called Bell's theorem. This, combined with experimental testing, is regarded by some physicists as restricting the kinds of properties that a quantum theory can have. The primary proposed implication being that quantum mechanics cannot satisfy both the principle of locality and counterfactual definiteness.